Gravity. It shapes the cosmos. It anchors our feet to the ground, governs the motion of planets, and sculpts the path of stars through the darkness of space. For centuries, it seemed simple and absolute, a gentle, invisible hand pulling everything together, an ever-present force that acts instantly, everywhere, all at once. But what if this enduring picture is incomplete? What if the true nature of gravity is stranger, subtler, and more deeply woven into the structure of reality than we ever imagined? To answer these questions, we must journey from the orchard of Isaac Newton, beneath the legendary apple tree, to the mind-bending insights of Albert Einstein, and beyond. To the cutting edge of modern physics, where researchers like EA Galperin are reimagining gravity for a universe defined by the speed of light and the fabric of space-time itself. Let's begin at the beginning. Newton's law of universal gravitation, one of the most celebrated discoveries in science. Newton declared that every mass attracts every other mass, with a force that grows stronger as the masses increase and weaker as the distance between them grows. The formula is elegant. The force equals the product of the masses, divided by the square of the distance, all multiplied by a constant of nature. This law explained the falling apple, the tides of the ocean, and the orbits of the planets. It turned the heavens into a clockwork machine, predictable and precise. Yet, hidden in Newton's description was a mystery. How does gravity act across the void? Newton himself called it action at a distance, a force that leaps instantaneously from object to object, regardless of how far apart they are. For more than 2 centuries, this view held sway. But the dawn of the 20th century brought a revolution. Enter Albert Einstein, whose theory of relativity transformed our understanding of space, time, and the very nature of reality. In Einstein's universe, nothing can travel faster than light, not matter, not information, not even gravity itself. This insight posed a profound challenge. If gravity cannot act instantly, if it must respect the cosmic speed limit, how does it really work? What happens to Newton's law when we acknowledge the finite speed at which information travels? This is the central question explored by EA Galperin in his groundbreaking research. To tackle this, Galperin turns to one of Einstein's own thought experiments, synchronizing clocks using light pulses. Imagine 2 observers, separated by a vast distance. To agree on the time, they exchange pulses of light, measuring how long each pulse takes to travel back and forth. This method anchors their measurements to the speed of light, weaving together space and time into a single, unified fabric. Galperin asks, what if gravity, like light, is a message, a signal that must travel across space, bound by the same rules? If so, then Newton's simple law must be revised. The transmission of gravity becomes an act of communication, subject to the delays and distortions that relativity demands. To describe this, Galperin employs the Lorentz transformations, the mathematical backbone of relativity. These equations show how measurements of time, distance, and even mass change depending on the observer's motion. When applied to gravity, they reveal a remarkable truth. The force of gravity is not the same for all observers. It depends on the relative velocity of the objects involved. Consider 2 objects hurtling through space at high speed. In Newton's world, their mutual attraction depends only on their masses and the distance between them. But in the relativistic world, the force becomes velocity-dependent. The gravitational mass of an object changes depending on the direction in which it moves. Transverse and longitudinal masses diverge. The result is a deformation of the gravitational force, subtle at everyday speeds but dramatic at velocities approaching the speed of light. This leads to a crucial realization. Newton's law is an approximation, valid only when velocities are low and distances are short. For the high-speed, high-energy universe revealed by modern physics, we need a new description. That description comes from Einstein's general relativity, which replaces force with geometry. In this picture, massive objects bend the fabric of space-time, and other objects follow the curves. Gravity is no longer a mysterious action at a distance, but a manifestation of space-time itself. Galperin's innovation is to bridge the gap between Newton's force law and Einstein's geometric vision. He introduces a tensor field representation, a mathematical language that captures both the classical formula and the corrections demanded by relativity. Gravity becomes a field, transmitting information at a finite speed, shaped by the movement of masses and the structure of space-time. This approach has practical consequences. Take the concept of the neutral gravitational point, the place between two masses where their poles cancel out. In Newton's world, this point is fixed as long as the masses don't move. But when we account for the finite speed of gravity, Galperin shows that the neutral point shifts over time. The change propagates at the speed of gravity, not instantly. This insight becomes vital for the precise navigation of spacecraft and satellites, where tiny errors can have big consequences. Galperin also offers a novel method for measuring gravity remotely. By placing a light source on a moving object and monitoring the light pulses received by a distant observer, we can infer the object's velocity and gravitational influence, without relying on reflected signals or lasers. This technique opens new possibilities for deep space missions and the mapping of gravitational fields across the solar system and beyond. Perhaps most fascinating are the illusions created by relativity near extreme objects like black holes. From afar, a falling object seems to slow and freeze as it approaches the event horizon, never quite crossing over. For the object itself, however, it plunges onward, crossing the boundary in finite time. This discrepancy is a consequence of the delay in information, a reminder that what we see is not always what truly is. So, what have we learned? Newton showed us the symmetry and predictability of gravity, a force that ties the universe together. Einstein revealed its deeper nature, a curvature of space and time, a dance of geometry and motion. Galperin builds a bridge, fusing the old and the new, grounding the abstract in the concrete, and offering tools to measure and understand gravity as it really is. Not an instant pull, but a message sent across the cosmos, shaped by the speed of information and the drama of relativity. Gravity, then, is not just a force. It is a conversation, a signal written into the very structure of space-time, obeying its own rules, always moving, always informing. With each new insight, we peel back another layer of the universe's grand design and discover that even the most familiar forces can surprise us, inviting us to look deeper, question more, and keep searching for the truth in the silent pull of the cosmos.